Recording software. All right, cool. So before anything else, like before we begin, we need to know who our enemy is, like who we are up against, right? Uh, the entire physics syllabus, right? So these are the lessons that you have ahead of you, right? So first is measurements. By the way, you should. I'm going to give you like a short note, right? So this is like the shortest note possible. I won't bore you with paragraphs of stuff. It'll just be equations and brief descriptions, right? So this is your syllabus, right? So first lesson is measurements. Second lesson is mechanics, right? Uh, third lesson is simple harmonic motion, uh, or oscillations and waves, right? And then fourth lesson is heat, or as I like to call it, heats. And then electricity, 6 properties of matter. So optics and stuff is inside waves, right? Because light is kind of a wave, but it's also a particle. But that's a discussion for another time. Okay, and then matter and radiation. Right. Then electric fields. Uh, Zoom out a bit. Hold on. You sent me uh, the teacher's guide, right? Let me just double check if everything anything has changed, because something is. That's all in mechanics. Um, you sent it to me in. Oh right, okay. I'm checking my email. Okay, give me a sec, just to confirm. Done. So hydrodynamics, all of that stuff is inside mechanics, right? Okay, I'm gonna have to kind of reorganize this a bit. Hold on. Sorry, false start. Sorry, my bad. So after heats, right, we'll actually be looking at gravity. Okay. Yeah, sorry. Sorry about that. And then electrostatic fields. Right. And then magnetic fields. You can also call this gravitational fields if you want, just to be complete. Right. So this section is when things actually get interesting, because you talk about force fields, right? Gravity, electrostatic, magnetic, right? Which is pretty important stuff, especially because it kind of helps you understand how the real universe works, which is really interesting. So that's when things actually get fun. And then you have current, electricity. Right? And then you have electronics. And then properties of matter. matter and radiation, right? Matter and radiation. Right, so there's 11 lessons, right? I'm going to skip the measurements lesson, right? I'm going to assume you're all right with that. So out of these, mechanics is probably the most boring, but also the biggest lesson, right? So it's probably where we're going to spend most of our time. But the questions that you get in your A levels, since you start off with mechanics, might be a bit easier by the time you actually do this question. So get really good at mechanics, because the reason it's taught first is because you need it in understanding some of the other stuff here. Like for example, in fields, especially gravitational fields, even electrostatic fields, you kind of have to have an understanding of how forces work, how forces cause motion and things like that, right? So all of that is taught in mechanics, right? But in my mind, mechanics is like, it's kind of boring, because it's just how things move, right? There's no understanding of like interesting things. The second biggest lesson, second biggest lesson is probably waves. So there you learn about sound and light, optics and all that stuff, right? And then it's heat and thermal physics, basically everything that has to do with heat, like how is heat transferred, how is it moved around and things like that, right? And then comes this set, right? 5, 6 and 7 are quite small lessons, right? But they teach you about fields, right? Basically force fields. Everything around us ultimately moves and interacts because of these kind of forces, right? So that's a pretty interesting thing. And then current, electricity and electronics are kind of like more of practical lessons, in the sense that they help you understand. They are more close to like engineering. They help you understand how electricity works, and then electronics, obviously it's in our phones, in our computers and things like that, right? So everything that has to be things like power and stuff come in like current, electricity. And then the last two lessons have to do with they're also not that big. They have to do with like like particle physics, things about material, matter and things like that, like what are things made up of and stuff like that, right? So we're going to start all the way over here. This is a bit of a big lesson. I'll try my best to cover it in like 1 month, hopefully, right? How much time do you have left? Exactly 1 year, right? August next year, right, is your A-levels, right? So yeah, it's about a year, right? Okay, cool. That's less than a year, because the year has 365 days. Yeah, yeah. So you said 332. Oh, right. Okay, sorry, I misheard you. All right. So mechanics will take about a month, I think. Hopefully, if I can rush through it. These set I'll try to finish in like 1 month, hopefully. And yeah, let's try our best to finish everything. And then next year, March, I'll actually be in Sri Lanka. So either I can come and actually teach you, or we can continue just zooming and recording these classes. But yeah, I'm actually excited also, because I get a chance to kind of go through all this material again. All right, so let's begin with mechanics, right? So mechanics. So here you will learn like the basics of forces and motion and things like that, right? Again, I'm going to start off telling you what's in this lesson, right? Give me a sec. My Zoom is annoying. Okay. Give me a sec. Okay. Hold on. Yeah, sorry about that. Right. So again, a breakdown of mechanics, right? What are we going to learn? First is we're going to learn about vectors, right? Um, and then we're going to learn about a little small note about graphs, right? So today I'm going to cover these two, vectors and graphs, because they help you kind of understand. They give you sort of the tools to understand uh, the inner workings in mechanics, right? So they're more like mathematical tools, right? To kind of understand motion and things like that, right? And so I'm going to cover that today, and then the rest is basically we're going to have translational motion. I'll just call that motion, right? And then we're going to learn about Newton's laws. Then forces, and then I'm going to talk about friction, then rotation, rotational motion, right? And then rolling motion, right? And then circular motion, and work, energy, efficiency, and then basically what you were talking about, hydrostatics and hydrodynamics. Right, so I'm going to start off a bit slow today, and just maybe cover two of these, and then we'll slowly speed it up as we go along, right? So let's talk about vectors and graphs. All right, so to begin with, what do you know about vectors? Mhm. Okay, cool. So the reason we are going to talk about vectors and graphs today is, like I said, they are mathematical tools that we'll be using to kind of analyze uh, basically not just motion, but later on you realize that uh, basically when it comes to forces and things like that, you get a lot of vectors involved in it. You said you really like math, right? So this is where kind of the mathematical aspect of physics really shines. But um, since there are people who do bio who do physics as well, they don't really go deep into the math. But since you're doing math, I will try to show you how it connects to, say, some of the things you're learning in pure maths, right? And show you the connections, because sometimes in the physics lesson they kind of gloss over the maths because there are people who do bio as well. But under having the kind of math understanding helps a lot, right? So the reason all of this is important, the reason we are starting here is because in physics we try to quantify things, right? We try to give things quantities so that we can measure them, right? And then once we can measure things, we can then create relationships between things and then build up equations and so on, right? So quantifying things is super important, which is probably why the first lesson that you actually start with is measurements, right? Being able to measure things and quantify them is super important, right? So when we are talking about quantities, there are two types of quantities that we can talk about, right? So put vector quantities, right, and scalar quantities, right? So you can actually put the heading here, we're talking about vectors, right? So like you said, a vector quantity has a direction, but the most important thing you need to know is that um, that's kind of what sets it apart between scalar quantities, right? So vector quantity has magnitude and a specific direction, right? Scalar quantities only have magnitude, right? So examples, right? So force is a pretty easy example, right? So you know that if you push something, it will go in a particular direction, right? So it's not only important to tell, okay, I'm pushing it with this amount of force, but it's also important to say, I'm pushing this in this particular direction with this amount of force, right? So whenever you describe a force, you need to talk about both its magnitude and its direction to fully describe a force, right? Because it does, like for example, if I have this and I throw it this way, right, and I'm saying, okay, I apply a 2 Newton force this way, it's not the same as if I apply a 2 Newton force this way, right? So um, to fully describe describe a vector quantity, you need to have both, make sure you mention both the direction as well as the magnitude, right? So other examples of vector quantities, you have velocity, right? You have displacement, and so on, right? Scalar quantities example, things like mass, right? So mass doesn't have a direction, right? So for example, when I say I have a mass of like 85 kilograms or something like that, right? So that doesn't have a direction, it's just a quantity, right? Another example is speed, right? And we'll kind of talk about the difference between speed and velocity, and distance, and the difference between distance and displacement as well. We'll talk about that later, but for now, just know that velocity is kind of the vector version of speed, and speed is essentially the scalar quantity, right? Another example of a scalar quantity is temperature. Again, you don't have a direction in temperature, you just have a quantity, right? A magnitude. Okay, so out of these, we'll be talking a lot about vectors, right? Because vectors are important, especially when you're talking about forces, because we need to know about direction and stuff, right? So let's learn a bit about some important mathematical ideas behind how to kind of talk about vectors, right? So first is we're going to talk about geometric representations of a vector. So how do you kind of represent a vector? Yes. That's actually the notation, right? Geometric is where, like, sort of, how do you kind of construct it in pictures, right? That's what you mean by a geometric representation, right? So simply it's just a you can basically describe it with a line and an arrow, right? That's how you geometrically represent a vector, right? And basically, this is the important part. The length of the arrow, length of the line, should be proportional to the magnitude. Right? So that's two things we need to describe, right? Magnitude and direction, right? Right? And then the direction is represented by the arrowhead, right? So that's kind of how arrowhead and angles, right? So for example, which angle this is going and stuff, right? So that's kind of how you sort of geometrically represent it. But now what you were talking about is also important, kind of the notation, right? So the notation we use is basically, if you can, let's say this is the starting point and the ending point, you can give the notation like this, right? Or you can give a notation like this, simple letter underlined, right? Or you can use a bold letter, right? So I can't really bold it here, right? So that's a A, right? So these are all different ways of giving different vector notations, right? So that's just basically how the, what do you call it, the convention we'll be using throughout all the lessons, right? So whenever you see a bold letter, simple letter, that would mean it's a vector. Or if you have just two capital letters like this with the arrow, that will tell you which direction. If you notice all of this, the reason why we are adopting like special notation is because we need to know whether a certain quantity is a vector or a scalar, right? And having this notation, as soon as you see it, you know, okay, this is a vector, right? Okay, so that's has to do with the notation and geometric representation. So based off this, you can talk about, I'll just ask a simple question like, what makes two vectors equal to each other? Yes, right? Same magnitude, same direction, right? But there's also a third thing that you need to keep in mind. Since we are going to talk about different types of vectors, right? So we'll be talking about forces, velocities, displacements, and things like that. You also need to make sure they're at the same type, right? So obviously you can't equate although they'll all be drawn with a line like this, right? With an arrow, one could represent a force, another could represent a velocity, but they won't be equal to each other in physics, right? In maths, since everything is abstract and it doesn't matter what physical things are, yes, vectors will all be equal to each other as long as these two things are met. But in physics, since we are dealing with physical things, right? Things like forces, velocities, displacements, you have to make sure they're the same type as well, right? Okay, so continuing on with some of the math stuff, right? The next topic we're going to talk about is multiplying a scalar, multiplying a vector with a scalar. What happens then? Yeah, so let's say the scalar that we are multiplying is a quantity like lambda. So what gets affected of the vector? So if let's say you have a vector AB, right? If you multiply this with a scalar quantity, will you get another vector back or do you get a scalar? Yes, correct. Right, so you get a vector. Result is a vector. Right, because we are just multiplying with a value, right? Just like 5 times the force, right? The magnitude equals magnitude of vector into scale. direction doesn't change, right? Because you're multiplying with a value that only has a magnitude but no direction, right? Okay. What happens if you if this scalar is a negative sign? Yes. So if lambda is is negative, right? Vector changes direction. Right? So how you would kind of write that is minus AB is going to be equal to B. Yeah. Okay. The next, okay, so I'm just kind of running through a lot of just simple basic math concepts, but they're kind of the building blocks that you need to understand more complicated questions, right? Okay, what do you mean? Okay, let's say you had two vectors instead of one, right? So there's an important definition that we need to know, and that's the angle between two vectors. No, so don't worry. In physics, you won't learn the dot product or the cross product. It's mostly in maths. So actually, if you can connect things back and forth between maths and physics, the mechanics lessons become way more easier, right? Because you will actually be learning way more complicated stuff in maths, right? So especially in applied maths, it will have to do a lot with like mechanics stuff basically, but so it will actually be easier by the time A level gets closer for you, right? So this is just a definition of what an angle between two vectors is, right? It's basically if you have two vectors like this, right? The reason I'm giving this definition is you can have two angles, right? There is this angle, which is like a larger angle, but usually you take the acute angle between the two vectors, right? In the case where you have two vectors like this coming towards each other, again you take this angle, right? And the other situation you could get is a vector coming like this and the other vector going like this, right? In this case, what you would do is so you can think of this as you can imagine sliding this vector this way, right? So as long as you don't change the magnitude and the direction of something, it's always going to be the same, right? So for example, sliding things around doesn't change the vector, right? So if you slide this vector this way, right, then you get this kind of situation, right? Vectors coming towards each other, right? So I'll actually give a small definition here. The included angle when vectors are coming towards each other, towards a single point, or away from a single point, right? So both these make sense, right? But this is the complicated part. You have one coming here, the other one going away, right? So the thing is, if you slide the one at the bottom, we'll get to that, right? But you need to know, okay, when I say angle between two vectors, this is what I mean, right? If the vectors are going away from each other, it's straightforward. If they're coming towards each other, it's straightforward. But if it's in a situation like this, you kind of slide it this way and take the angle between that, right? Again, like it's just a measurement, right? So this is to kind of standardize things, right? I mean, it's completely up to you, right? If you wanted to, you could measure this angle, right? There's nothing stopping you from doing it. But if everyone follows the same standard, it becomes easy, right? So this is kind of like standardizing it and using kind of what we call a convention, just to make things easy, right? Again, there's no theory or anything like this. It's just we're talking about the notation we'll be using, right? So that we can be consistent throughout. But now comes what you asked about, right? The resultant, and this is important, right? Can you tell me what the definition of a resultant is? Sorry. Yeah. So it's a single vector, right, that represents a system of vectors of similar type, right? So how do you write that? A single vector that represents a system of vectors of similar type. Right? So the important thing you need to know is the resultant doesn't change the final effect the system has, right? So let's say the system has multiple forces acting on it, right? The resultant has to represent all three of these, right? And it has to be equivalent to the same thing, and the final result is as if a single force, okay, in this example, imagine these are forces, right? So there's multiple forces acting on it, and then this single force does the same thing that all the three of these forces do, right? Yeah. So how do you find the resultant force is the next question, right? So to help you do that, again, we'll be talking a bit of maths, right? And yes, right? So we need to know the laws of vector addition, right? Because what you're doing here when you're finding the resultant is kind of adding them all up and figuring out which final what single vector can represent all three of them, right? So there is kind of an addition involved here, right? So the question is, how do you add quantities that both have magnitude and direction, right? We know that 2 plus 2 is 4, right? But here we are only dealing with sizes, we're only dealing with magnitudes, right? But now we are dealing with both magnitudes as well as direction. So we need to know how to add quantities that have both of those things, right? So you're correct. The first thing we're going to learn is the triangle law, right? So you will notice that we are going to use the help of geometry, that is just drawing diagrams and things like that, right? So if you can kind of organize your vectors, slide them around and create a triangle, right? Like this. This will be your resultant. I'll call this vector A, vector B, right? A plus B is going to be R. Right? Another way of writing this is AB plus BC is going to be equal to AC, right? So the important thing is you need to know when you're doing this is make sure you understand that this guy is um, this guy's head is at this guy's tail, right? So you have to kind of organize it in this order, right? They have to you just have to be aware of the directions, right? Because directions also matter, right? So always remember that it goes like this, and then the resultant will be going from A to C. Can you see my cursor? Or do you only see it? Okay, only when I draw. How about now? You can't see it now? Okay, so I'll just then draw. Okay, so you start from A, you go to B, and make sure that they are touching each other in this particular order, and then your resultant will come in this order, right? So kind of put this image in your head, especially the arrows, right? So this is called the triangle law, right? And it kind of makes sense, right? Because if you think about it, if you're actually, I'll use the other the parallelogram law, and I'll explain why it makes sense, right? So parallelogram, right? So in this case, if you had your vectors like this, hold on, try to draw straight. That's not so hard. Okay, cool. Right, so imagine you had one vector here and one vector here, like this, kind of going away from each other, right? The resultant would be basically if you complete a parallelogram, right? Like this. That is, this side is parallel to this side is parallel to this. Your resultant will be the diagonal. And then that will be your resultant. Okay, so this I think makes sense. Again, I'm going to use a force as an example, right? So imagine imagine there was some sort of like yeah, so imagine you had for some weird reason a rock and two pieces of string like this, right? And two people are pulling the string like this, right? But what's going to happen to the rock? It's going to move this way, right? Yeah. Is there a better example? I can't hear you. No. The people aren't. No. People aren't moving. The people are here, standing still, and they are standing still, and just pulling the string. The rock is. No, it's gonna move. What? Okay, maybe bad example. Let me think of something else. No, car has wheels. Okay, let's say there's a bed, right? And you're trying to move a bed, right? And I'm thinking of this because I've been moving for the last 2 days, right? So it's bed. Let's say two equally strong people push the bed from two different angles, right? This way and this way, right? What's going to happen is if you slide these vectors around, you can get a force in between them, right? And then depending on the size of these forces, right? For example, if this force is larger than this force, this diagonal will be closer towards this one than this one, right? So the important thing I'm trying to say is, whenever you're learning like mechanics or any other part in physics, try to actually visualize what's going on, because everything has a physical kind of um, impact in terms of like how you can kind of understand it, right? Unlike in maths where some of the things are abstract, right? So try to kind of visualize what's going on in your head, especially when you're doing questions as well, right? Try to draw diagrams and try to understand what's physically actually happening, and that becomes really helpful. Okay, so that's the parallelogram law, and now the important thing you can note here is it's pretty much the same as a triangle law, right? Because if you slide this vector over here, what do you get? Like if you basically slide this vector, you get the triangle law, right? So so they're essentially kind of related to each other. Then comes the polygon law, right? Which is basically, if you had a bunch, the polygon law, right? Yeah, you probably won't need it, right? But just to be complete, let's say you had a bunch of vectors, right? Yeah, you do it in maths. Yeah. If you have a bunch of vectors, like this. So if you again keep them head to tail, right? Like this, and then the final vector that will kind of complete all this will be your resultant, right? Okay, so yeah, that's how you kind of add them all together. So so that's about addition, but what about subtraction, right? Yes, so it's basically subtraction is basically change direction and add, right? So it's the same as addition, but you just change the direction. That's it, right? So if you had a vector A minus a vector B, all you have to do is take vector A and add it to minus vector B, right? Which is just change in direction. Which we talked about already. Okay. So we learned about vector addition, we learned what a resultant is, right? Now let's learn about how to find the resultant, right? Finding the resultant. Yeah. Good, right? So one way we can do it is graphical or geometrical, right? So there you'll basically have to draw everything, right? So you have to draw everything to scale, right? Draw everything to scale. Right, that means, okay, actually I'll just go back a little before. So I was telling you about how when you are representing a vector geometrically, the length of the vector, the length of the line should be proportional to the magnitude, right? So for example, if you had a 10 Newton force and each Newton is represented by 1 centimeter, you'll have a line that's 10 centimeters long, right? So what I mean by that is, what I mean by when I say draw everything to scale, you draw everything proportional to the actual quantities, and then arrange them according to triangle law or parallelogram law, and measure the result. Yeah, triangle law, parallelogram law, or polygon law, right? And measure the result, right? So that's, you have to actually draw it. You have to take a ruler and you have to figure out a scale, and that's kind of annoying, right? We need a better way of doing it, right? So the next way we can do it is analytically, right? So we don't actually then have to use a ruler or anything. We can just draw like rough diagrams by hand and kind of use the equation that you just mentioned to kind of calculate them analytically, right? So let's learn how to do that, right? So let's actually derive the equation that you talked about and see how that equation actually comes about, right? So let's say we had two vectors that we want to add, right? So we have vector p and vector q, right? And the angle between the two vectors is theta, right? And then we have the final resultant, right? And the resultant's direction is alpha, right? So here the direction will be given in terms of an angle, right? Because we need some sort of way of saying, okay, this is the direction we're talking about, right? So basically what we want to find is, we want to find r and we want to find alpha, and we've been given p, q and theta, right? So r and alpha is what we don't know, right? Because if you are going to find the resultant, it's not just important to tell the magnitude, but we also need to give a direction, and the only way we can give the direction is using an angle, right? Yeah. We can use like north, east, west or something like that as well, but it's easier to give an angle, because then what we can do is we can say it's alpha away from p or whatever, right? Okay, so what we're going to do is we're going to slide this around. Now you can do this using the parallelogram rule as well, but we're going to use the triangle rule, right? So simply slide slide q over here so that we have a nice little triangle, right? And then the r resultant will be over here, right? And that angle is going to be alpha. Okay, so now I'm going to do a small construction. I'm going to create a 90-degree right angle triangle, right? So what I've drawn in green is just a construction, right? I'm going to name this A, B, C, right? I'm going to call this new point that I just constructed D, right? Can you tell me what this angle is? This angle over here. Oh, okay, you can't see. If I draw it like this. No. Okay. So if you, okay, so where did we okay, so theta is this angle between this and this, right? So imagine I slit this AB along here. I get the same diagram, right? So what is this angle? It's still theta, right? Because if I, yeah, because the angle between P and Q is theta, right? So this entire line here, like for example, this is Q. If I take AB and I slit it like this, right? But this is the same as this, right? Yeah? Is that alright? Yeah, so this angle is theta, right? A bit confusing. This is Q, right? Yeah, so what we're going to do is we're going to use good old Pythagoras theorem, which basically says the hypotenuse here is going to be equal to this squared plus this squared, right? Because we have a right angle triangle here, right? So r squared is going to be equal to AD squared plus DC squared. Cool. Alright, so AD is actually equal to P plus this part, right? So this part, yes, is Q cos theta. So P plus Q cos theta squared is what AD is. DC is Q sin theta squared. Cool. So if you expand this, it's P squared plus Q squared cos squared theta plus 2PQ cos theta plus Q sin squared theta. So this becomes Q squared, right? Yeah, so you know that Q squared, yeah, I take, yes, so you have Q squared cos squared theta plus sin squared theta. This becomes 1, and then you have 2PQ cos theta. And now you know that you get the equation, your resultant is equal to P squared plus Q squared plus 2PQ cos theta squared root, right? And that's how you get that equation using. Cool. But it's not just enough to know the magnitude. So this is the magnitude of R, right? This is the magnitude. We also need to know, we need to also figure out what alpha is, the direction. So for that, what we're going to do is we're going to look at the tan value of this alpha, right? So if I look at tan alpha, it's just going to be opposite over adjacent, right? Which is DC over AD, right? So DC again is Q squared, sorry, Q sin theta, right? And AD is P plus Q cos theta, right? And that's your tan alpha value. So alpha is going to be equal to tan inverse Q sin theta P plus Q cos theta. So this gives you the direction. Cool. Okay, so some important things, right? What happens if this theta is equal to 0? Just to make things, just to show you some special cases. If theta becomes 0, right? Yeah, cos theta becomes 0, right? Yeah. So this entire part becomes 0. Yeah, so your r squared is just going to be equal to p plus q, and alpha is going to be equal to 0 as well, right? Because if theta is 0, p is going to look like this, and then q is going to look like this, right? So the resultant is also going to be on the same line. Does that make sense? If theta is 90 degrees, no, sorry, yeah, my bad. Yes, yeah, cos 0, so cos goes like this. Oops. Yeah, so cos 0 is 1, cos 90 is 0. So what you would get is a nice right angle triangle. If and then you'll just get the usual r squared equals p squared plus q squared, right? If theta is 180, you just get p minus q. Yeah. So again, that kind of quick, if you can remember those things, they'll be helpful when you are solving questions really fast, right? Just like special cases. Along with that, you kind of already know this. Resolution of vectors. Right, so that's basically how do you describe this? Resolving a single vector into its perpendicular components. Which is basically kind of like the reverse of finding the resultant. Yeah. So you already kind of I'm talking about in a situation of just the act of resolving, right? So kind of breaking it into its components, right? So you have your x component, which is r cos theta, and you have your y component, which is r sin theta, right? So the act of resolving it is just breaking it into components, right? You're always mentioning like basically the next section. So what you just mentioned is based on the next section, which is basically finding the resultant of a system of coplanar vectors, right? This word coplanar is important because you can only do this if everything is in the same plane, right? So imagine you had a bunch of vectors like this, just a system of vectors, right? The first step that you need to do is you need to kind of extend them like this, right? And kind of bring them all to a single point, right? So step 1, bring them to a single point. Right, so basically this is that, this becomes that, and then this becomes that, right? So these are the same couple of vectors that I've kind of brought into a single point over here, right? And then what you do is step 2, resolve each vector into resolve each vector to its x and y components, right? So you had a bunch of vectors, you put them all into a single point, which is basically sliding those vectors. Remember, sliding is allowed, but as long as you don't mess with their direction or you don't mess with their size, right? So once you get them all into a single point, you break them into their components, just like we talked about here, right? So what you will get then when you break them all into components is you'll get all the so you have two vectors like this. You'll get all the vectors along the x and y directions, right? So you'll get, for example, if you break this this vector, you'll get a vector like this and a vector like this. If you break this vector, you'll get a vector like this. I will actually use a different color. If you break this vector, you get a vector like this and a vector like this, and this won't exist anymore, right? If you break this, you get another vector here and another vector here, and this won't exist anymore, right? And then this, you break it here and you break it here. You get the idea, right? It's getting kind of messy, but you'll end up with just x and y components, and what you then do is kind of add them all up. Since they're in the same direction, adding them is easy, right? So what you will get is one big vector in the y direction and one big vector in the x direction, right? When you add them all up, they don't have to be in the same direction. For example, it could end up like this, right? It could end up like this, or it could end up like this, right? Depends on the sizes of all these, but I'm just going to just generally draw it like this, right? And once you do that, imagine you had a vector like this, right? You can kind of slide them along and use the, so that's step 4. Use triangle law. Right? So you kind of slide them along, and then you get the resultant like this. So R is going to be equal to x squared plus y squared. Yeah, so the thing is, you've broken them into right angles, right? So it's always going to be a right angle. X and y components, I'll just put in brackets here, perpendicular, right? When I mean break into components, resolving, it means resolving into perpendicular components, right? So automatically it just becomes Pythagoras rule. By the way, I'm not going too fast or anything, right? Okay. And that's it for vectors. We are done. So we learned what a vector is, we learned about how to add them, we learned about their resultants, how to find them analytically. Then we learned, okay, what do we do if we have a bunch of them? We kind of bring them to a single point. We break them into perpendicular components, add all those components up, and use the triangle law. Right? So that's all the vector knowledge you really need in physics. Right? So let's go back to this. Vectors done. Right? So now let's quickly talk about graphs. This will take maybe 10-15 minutes. Right? And then we can wrap up for today. Okay. By the way, I'm sorry if I'm a bit boring today because I'm really tired. We've been moving house for the last 2 days, and it's night, and my brain is starting to die. So no, I'll finish this. Just this will take like 10-15 minutes. So we'll quickly talk about graphs, and then that will kind of complete all our tool set that we'll be using for the rest of the lesson. Right, so first concept is coordinates. Kind of already know what a coordinate is. So we have x and y coordinates in a graph, right? So this represents x and this represents y. So graphs are super important in physics because, again, we're dealing with quantities, right? And if you can graphically represent quantities in a graph, you can find relationships between them, right? And then you can see, okay, for example, if do you have a dog or a cat? Okay. So for example, if you measure how much food you give your cat, right, and how fat your cat becomes, like the cat's weight, right, and if you kind of plot those values, you will see the more food you give it, the more its weight increases, right? So then you can create an equation for your cat's weight. Like if you say x is the amount of food you give and w is its weight, you can kind of find a relationship between them. So again, we are coming back to this idea of quantifying things, right? We try to measure things and we try to create quantities, and then graphs help you kind of visualize how those quantities are related to each other, right? And how those relationships are formed, right? And in maths, you learn a lot about how to find, for example, the slope of these graphs, the areas of these graphs, and things like that. And we learn now how each of those quantities will kind of help you understand different relationships between these values in a graph, right? So so we understand what coordinates are, and then you know what intercepts are, right? So for example, I'm just going to use the same diagram. Say we had a graph like this. This will be the x-intercept, and this will be the y-intercept, right? So basically we write, so at the y-intercept, x is equal to 0, right? At the x-intercept, y is equal to 0. Okay, so these are all pretty basic stuff, but now comes the important, very, very important term, which is the gradient of a graph. So what's the gradient of a graph? Okay, so that's like a mathematical definition of it, but what is it really? What are we really trying to measure with a gradient? Okay, so just to get a feel for what we are actually measuring in a gradient, we are actually trying to figure out the slope, right, of a graph. or a function that we're plotting. Right. So we are going to describe that slope using the tan value, right? Why is that? Because the tan value captures the angle, right? And the angle tells you kind of the slope of something. So just to give you an idea of how to kind of derive this, so imagine we had a XY coordinate frame and then we had a graph, right? Something like this, right? So if I wanted to find the slope at this particular point, right, that is how steep is it, right? What I would do is I can kind of construct a tangent to that point. So how to draw a straight line, right? So imagine that's actually a straight line, right? Tangent. So this is the point that we want to find the slope of, right? And let's say the x and y values of the x and y values of that point. This is y, and this is x. Call this capital Y and capital X. Okay, cool. So we want to find the slope of this point, like how steep is that point, right? So we are going to imagine you take a small increment forward, right? I'm going to call that delta x, right? So imagine, for example, if this is 5, this is 5.2 or something like that, right? And I'm going to, sorry? This is actually, that's a good point. This is all connected to calculus, right? So differentiation, I'll kind of explain the connection after this, right? So imagine you get a small increment delta x this way. That's going to cause a small increment in the corresponding y direction, right? So what I'm going to do, so what am I after? I'm trying to find a way to describe the slope of this graph, right? So, and the technique I'm going to use to do this is I'm going to try and figure out the tan value of the tangent to this point, right? So to do that, I'm going to increment the delta x value forward and take the corresponding delta y value in the y direction, right? And I'm going to construct a small triangle here, right? And then there's this value called theta here that I'm going to measure, right? So tan theta is going to be this divided by this, right? So this is going to be delta y, this is going to be delta x, right? So tan theta is going to be delta y by delta x is going to be this tan theta value, right? But does this really represent the slope at this point? No, yeah, because this is where calculus comes in, right? So you learned about differentiation, right? So the idea behind differentiation is pretty much this, right? So what you're doing is imagine this delta x becomes smaller and smaller and smaller and smaller. So the smaller this becomes, the more this line comes closer to this actual curve, right? So this is the tan theta value. The gradient, right, is basically tan theta as delta x approaches 0, right? So why are people obsessed with this slope? why do we have this entire branch of mathematics called differentiation to kind of do this? Because it captures the most important relationship between these quantities. It captures how basically it captures the rate of change of y with x, right? Because the slope tells you, okay, if, okay, for example, if there's a small change in x, right? If there's a small change in, if you make a small change in x and y increases suddenly, right? What will the slope look like? It will look like this, right? It will look really sharp, right? A small change in x is going to cause a rapid change in y, right? It's going to cause a rapid change in y. But if a large change in x causes a small change in y, the slope will look quite different. Yeah, so understanding how the slope works helps you understand pretty important relationships between quantities. Again, for example, like let's say you feed your cat a little amount of food and suddenly its weight explodes and it becomes obese, right? Sorry, I'm not fat shaming your cat, but imagine like you just feed a little bit, and then imagine the other way is true, right? Like you feed it a large amount of food but its weight doesn't change that much. You can kind of understand what is happening there by looking at this graph and kind of visually seeing, okay, if I look at the slope, I can talk about how quickly y is changing with x, right? How y is affected by x, the rate of change of y with the rate with x, right? Which is why differentiation is super important. And just keep that idea in your head when you're doing maths, when you're doing physics, because when we deal with definitions like velocity, for example, right, what we are getting essentially is the rate of change of displacement with time. So what you're then, yeah, so all you're doing is really differentiating, yeah, right? And we'll talk about integration is kind of finding the area under a curve, right? So that gives you different physical meanings as well, right? So kind of connecting all those dots becomes super important, and it will help you do questions mostly, right? So slope of the graph, another form, so just keep in mind the idea of slope. Keep in mind that it gives you the rate of change of y with x. Another way of kind of defining it more, kind of the way you defined it at the start, just like the official definition, it's the tan value of the tan value of the angle the tangent makes with the x-axis. Yeah. Right. Okay, so that's really this becomes super important, right? The gradient. So much so that there is an entire branch of mathematics just to finding gradients. Right? So this is basically differentiation. Next is the area under graph. So if you have a graph like this, right, this is what we call the area under graph, right? You could also have negative areas. For example, if you have a graph like this and your area is actually down here, right? The positive value in the x and a negative value in the y, this area will be a negative area. Right? Here both are positive, right? So that's area under graph. Just to wrap up, we'll just I think it's really important to get a feel for what's happening in graphs, like be able to look at a graph and kind of describe what's happening to the quantities. Right? Again, we are talking about the maths and the kind of the intuitive understanding of these things, so that we can then use them in the rest of the lessons, right? So we're just going to talk about the behavior of these graphs, right? So the first thing we're going to look at is the behavior of the coordinates of a graph. So what I want you to do is, once we are done, go through these notes and kind of put them, like embed them deeply in your brain, because when you look at a graph, you should be able to describe it really quickly, right? So the first thing is, we are going to look at the coordinates, like what's happening to the coordinates here, and describe them, right? So we have x, y. First one is just a very simple graph like this. Can you tell me what's happening to the coordinates here, right? Especially in all these examples, we're going to look at x increasing. Okay, so they are proportional to each other, right? So how a complete way of describing is basically positive y coordinates, right? Positive y coordinates are the y coordinates increasing or decreasing? Yeah, so y coordinates are increasing. What can you tell me about their rate? Correct, right? So they are constantly increasing. Increasing. I'm going to put this in brackets, at a constant rate. Right? Cool. So in this same format, can you describe what's happening now? Okay, the way you have to think about it is, imagine you're climbing. There's a tiny Zuleika walking along this. What's happening to the slope? Yes, so positive y coordinates are increasing at a increasing rate, right? So this was a constant rate. The slope is not changing. Here the slope is increasing. Yep. What about this? Tell me what's happening to the rate. Again, it's positive y coordinates increasing. What's happening to the slope? Yes, at a decreasing rate. Right? So there's two things you need to be aware of, like what's happening to the y coordinates. They're increasing, but they're increasing at a decreasing rate. Right? And that's determined by the slope. And to kind of show what happens with negative coordinates, right? So if this is x and this is y, if I had a graph like this, what does this mean? depends on how you describe it. If it's positive y coordinates, they're decreasing at a constant rate. Or you can describe it as negative y coordinates, increasing at a constant rate. Right? Just do one more. Right? What about this? Again, the negative y coordinates, increasing. Yes, correct. Right? At a decreasing rate. Cool. So that was basically the behavior of coordinates, right? Basically how y is changing. Right? Let me know when you're done copying. Okay. Now behavior of the gradients. Okay. So what can you say about this? About the gradient. Now we're talking about gradients. Right? Yep. Zero gradient. Right? No slope. What about this? Sorry? No, just this. Yeah. So constant. It's a positive gradient. Okay. Positive. Because the angle that is making here is acute angle, right? So there's a constant positive gradient. How about this one? No, tell me, just describe what's happening to the gradient. Yes. Correct. Right? Constant. Negative. Gradient. What about this? Yeah, gradually increasing positive gradient, right? How about this? Correct. Decreasing positive gradient, right? How about this? Imagine what's happening as you walk down the thing. What's happening to the negative gradient? The negative gradient is decreasing, right? So gradually decreasing so it's decreasing negative. One last one. This. infinite gradient, right? So the slope is infinite. Yeah. One last section about behavior of areas, right? Of areas. Right? Areas under the graph, right? So not just any areas. Okay, so add something like this. Right? Imagine x is increasing. This will be a constantly increasing positive area. This is a positive area No, think about the area. Is it constantly increasing, or is the area every time you keep going here, the slice of area that you're adding increases, right? So positive area increasing at an increasing rate. And positive area this one is tricky. Can you figure this one out? Correct. Positive area increasing at a decreasing rate. And the last one, negative area increasing at an increasing rate. Cool. And we are done with graphs as well. All right, so we'll wrap up there, and then next week we'll talk about basically the equations of motion and Newton's laws, and maybe forces, and try to cover this section next week. Friday should be alright next week. I can do Saturdays also. I'm okay with Saturdays. If you're okay with Saturday. Yeah. Sure. Yeah, no worries. Yeah. Okay. So as if that was a lot of material, but yeah. But it was also a lot of basic stuff. So it should be alright. Cool. Yeah, so next week we'll actually get into the actual mechanics stuff, now that we have all the tools. Alright man, try to find a paper class. I'll keep bugging you till you do.